1. And then second half of class, for last 15 minutes, I'll go over volume surface area, and then I'll also go over shadow problems. So I want to focus on those two. I think we did all the other ones yesterday. Okay, so extreme value theorem. We're moving into chapter 3. Obviously, this is not going to be on the quiz tomorrow. There is homework for 3.1, but homework is due on Thursday. I'm not checking homework tomorrow. Okay, so extrema. Extrema is another word for max and mins. Max and mins are the peaks and valleys of our graph. Now, we call these relative max and relative mins. Hills of the graph are relative max. Valleys of the graph are relative min. It's another hill. So 2 hills, we have 2 relative max and 1 relative min. We also have something called an absolute maximum. Absolute maximum is the highest physical point, highest point on the entire graph. So this point is not only a relative max, it's also an absolute max. It's the highest point. We call it a relative max or local max because relative to the points near it, it is the highest point. But it is also an absolute max because over the entirety of the graph, it's the highest point on the graph. Now, this graph has a relative min, but it does not have an absolute minimum because absolute minimum would be negative infinity, and negative infinity is not a physical point, so we don't consider that an absolute minimum. Okay, closed interval. When I have a closed interval, that means my graph is have the endpoints defined. This point is a relative minimum, but it's also an absolute minimum. Right, relative because it's a value of the graph, but it's absolute minimum because there's no other point lower than this. This point here is called an absolute maximum because over the entire interval here, this is the highest point. But there is no relative there's no relative max. Because it has to be a hill or valley of the graph. So here, there's nothing on the other side, so it can't compare with both sides. So this is an absolute max, but it's not a relative max. Okay, so along an open interval, if the graph has open points or open circle, again, there is an absolute minimum and relative minimum, but there is no absolute maximum because a hole means that the graph will get infinitely close to that point without ever reaching it. So if I choose a point that's close to it, you can always choose a point even closer. So here, this is what we can consider no absolute maximum. And again, holes and plus and minus infinity cannot be considered as absolute extremes. Okay, so today the topic is involving extreme value theorem. Extreme value theorem means the whole point of extreme value theorem is to find the highest and lowest points on the graph, or the highest and lowest y value of the graph. If a function is continuous and on a closed interval, then it has both an absolute minimum and an absolute maximum on that interval. So if a function is continuous, then the absolute extrema will either be at critical numbers or at an endpoint. So here's a quick example here. Here's a visual example. We only have to consider, if the graph looks like this, we only have to consider the endpoints and the critical points. So critical points is wherever the slope is either 0 or undefined. There's no other points that could be the highest or lowest points on the graph. It's always going to be restricted to just the endpoints and critical points. So the way you find these critical points, you have to go to the derivative. So we're either setting the numerator of the derivative equal to 0, or we're setting the denominator of the derivative equal to 0 to find our candidates. Okay? It doesn't mean that all the candidates are guaranteed to be absolute max, absolute min, but we call them candidates because they are important enough for us to test. So here's what we're going to do. We're going to find f prime. Set the numerator of f prime equal to 0 to find a point that could look like this, where the graph is a smooth transition. But if there's a denominator, we also want to set the denominator of f prime equal to 0, because that will lead us to a sharp turn. A sharp turn is still a point that we have to consider because it could end up being the lowest or highest point in the graph. Bottom of the page here. Relative extrema only occurs at critical numbers, but not all critical numbers are where relative extrema occurs. So what that means is this. Just because I have a slope 0 doesn't mean that it's a relative max or relative min. It's possible, but a slope 0 could also be where it flattens out, but it doesn't change direction. Okay. Max and min values refer to the y values at that point. That's important. Okay. So we're going to just go to the next page. Try examples 1, 2, and 3, and then we'll do review. Okay. Okay, so here are the steps. We're going to confirm that our function is continuous on the closed interval. Then we're going to find critical points. Okay, set f prime equal to 0. Set the denominator of the derivative equal to 0. So we want to always make sure that we look in both places if there are variables above and below. After we find all of our candidates, then we plug into the original function and compare the y values. Okay, whichever has the highest y value is your absolute minimum maximum value. Whatever is the lowest y value is your absolute minimum value. Okay, so let's look at example 1. Find critical numbers. What are the values of the absolute extrema? So our function is this is a nice polynomial. So polynomial has no breaks in the graph. The domain is always negative to positive infinity and never has any poles, no asymptotes, nice smooth curve. There's no variable in the denominator. So you never have to worry about continuity with polynomials. But it's still important that we name the condition. I'll be looking for this on your test or quiz. We have to establish our condition. Pretty much every theorem that we're going to see has this first step. Establish continuity. Okay, so we're following the steps here. Confirm continuity. Next up, let's find the derivative. We have endpoints to test. but we're going to see if are there critical points that we need to test in addition to these endpoints. So we go down to the derivative level. We're going to look for slope 0 by setting the derivative equal to 0. So what are our critical points? What do we get if we set this equal to 0? Just 0, right? If I set x minus 1 equal to 0, I'll get. So it looks like I have 2 critical points. But how many numbers are we going to test? 3, okay. There's a duplicate, so we only need to test 0 and 2. And what is it about 1 that we know that we should test this as well? You talk about the location of that value. That is important. Good, it's on the interval. So we always have to keep reminding ourselves, sometimes you're finding these critical values that's outside the interval. If it's outside the interval, then you're not going to use it, okay? Because we're only concerned about our interval. So it's possible that you find all these critical numbers and none of them fall inside the interval. That's okay. That means you're only needing to test your endpoints. So your endpoints, you always test endpoints, and you may or may not test critical points depending on whether they fall inside the interval. Okay, so here we'll test 0, 1, and 2. And they all go back into the original equation. Okay, f of 0. F of 1. F of 2. Okay, now we only look at the y values. Okay, what's the absolute max? 16, okay. We don't care about where the x value location is. So we'll say absolute max value is 16. And what's the absolute minimum value? -1, yeah. On the in your textbook, they do present absolute max and absolute min as ordered pairs, but on the AP exam, they care about the y value. They don't care about the x. Okay, so the whole purpose of extreme value theorem is what is the minimum amount of information that we can gather to find the highest and lowest points on the graph without looking at the graph. We're just relying on algebraic methods. So we target the endpoints, we target the critical points, and we test them all. Whatever's the highest point is our absolute max. Whatever lowest point is your absolute min. Okay, so let's try example 2. The function has no denominator, so I think we're pretty safe. Our function is continuous on the closed interval. We have our 2 endpoints, which we're going to test, but we're going to find our critical numbers. Okay, what rule do we have to go through to find the derivative? Chain rule, yeah. Outside, inside. So outside's derivative 2/3 parentheses to the -1/3 times the inside derivative. Do some cleanup. Okay, we want to set the numerator and denominator equal to 0. But is there anything in the numerator for us to find? No. If we set 2 equals 0, it doesn't make sense, right? There's no variable, so we can ignore the 2, and we can just look at the denominator. Now, anytime you set the denominator of the derivative equal to 0, you're basically looking for slope potential candidate. Do both sides. So I have x equals 1 as a candidate, but do I test it? Do I use it? Why not? Okay, it says not inside the interval. Okay. Now, it is the right step for us to look for it, and we found it, but if it's not inside the interval, it's not going to be used. Okay, but it's still important that we look for them in the right places. So, how many points are we going to test then for absolute max, absolute min? Just 2, right? Just the endpoints. So comparing these two values, absolute max is cube root of 4. And absolute min is okay, any questions here? Okay, number 3, last one. Our function, there's no denominator. We should be safe. So our function is continuous on the closed interval. I'm gonna put this on a separate sheet. Okay, we are going to test the endpoints, but we'll save that for the end. We want to find the critical value. Critical numbers means we got to go to the derivative. To get to the derivative, what's involved with this process? Product and chain. Good. All right, so let's set it up. chain rule here. Outside's derivative. Times inside's derivative. Okay, good so far? Okay, so now the messiness is gonna come with having to combine these two fractions together, common denominator, so that we can get a numerator denominator all nice and clean, so that we can look for critical points in the numerator and the denominator separately. Do some reducing along the way. I see the 4 and 2 numerator denominator. I'm gonna just take one of those out. I'm gonna put all this in their right places in terms of their numerator and denominator value. Any questions with that so far? I'm kind of doing a couple of things all at once to try to get that to be a cleaner fraction. Okay. So now, we do need common denominators. What's our common denominator here? Yep, that's right. I need both of them. This one contains a 3 as well, so that's perfect. Okay, look for differences between the old and new denominator. This one, it has additional 3 minus x to 1/2, so I need to balance that with the numerator. If I multiply these together, I'm essentially doing square root times square root, which will leave me with just 3 minus x. Okay, any adjustments here? No adjustments, so it's easy. Okay, so this is 12 minus 4x minus 2x. Okay, so here's my cleaned up derivative. Good, so all that work, now we can look for critical points. We'll set the numerator equal to 0. We'll set the denominator equal to 0. Okay, I found 2 critical points. I have 2 endpoints. We test everything. Yeah, 3 is a duplicate, but technically we are still testing it. 2, okay. We're not always going to test every interval, but if it's inside the interval, then we do test it. So you have 3 candidates. We have 3 is a duplicate, 0, and 2. So they all go back where? Good. We're looking for physical locations now. No more derivative. Okay, we only care about the y value. Absolute min is 0. absolute max is 8/3. Okay, question. So in your packet, real quick, begin, turn to page towards the back. Starting on page 15, I have summary of each of the theorems. You're going to see summary of 3.2 mean value theorem, Rolle's theorem on each page. So let me just kind of go through the big purpose here, big idea that we've accomplished. So the purpose of extreme value theorem is to find the absolute max or absolute min on the closed interval. We always have to make sure we establish our continuity statement. So we always have to say function is continuous on the closed interval. Now, if there was a hole or asymptote that affected the interval, then we stop the problem and say the function is not continuous on the closed interval. EVT doesn't apply. We saw it with IVT, with unit 1, and some of that carries over. So we know absolute max, absolute min can come from the endpoints, so we're definitely remembering to involve them. But the calculus comes in when we find critical points. So we find the derivative, set the numerator equal to 0, set the denominator equal to 0. Doesn't mean that we're always going to find critical points, top and bottom, but we always want to make sure we look. And then we test critical points and endpoints into the original function, assuming that the critical points do fall inside the interval. So we always continually checking with our interval to make sure that it's still part of the problem, right? If it's outside our problem, then we just ignore it. And then make sure that you're inserting your candidates into the original function. And you only care about the y value, so we can just ignore the x value here. Okay, so that's it. It's not difficult, but sometimes the derivative can get messy. You got to go through like what we saw, product and chain. But we'll definitely spend some time reviewing over this on Thursday as well. Okay. There is homework from the 3.1 packet that you picked up from the textbook, but that's due on Thursday. Okay, due on Thursday. Okay, so let's go to your test, or sorry, your quiz review, and let's go to page 7. I just want us to do number 8 and number 10. Sure. Page 7 in your review packet. Okay, try number 8. See if you can work through this volume surface area problem. Yeah. And we try a large triangle. So I say the height of a small triangle is to the height of a large triangle as the base of the small triangle is to the base of the large triangle. So
Then I would do I don't know. I got this. But it's on that.
So we talked about how for cylinders, the radius, I use different variable because maybe it's all again. But we talked about how the radius of the cylinder is a constant. So we just replace that with, because that's the radius of the. It tells us that There it is. The tank has a base area of 400 square feet, so it tells us that this circle, its area is 400 pi.
Mhm.
So if the area is 400 pi, I can work backwards and so on.
So you just replace this like this.
Yeah, you can use R if you.
And then what is this formula?
Oh, this is pi, this is pi r squared h.
Mhm.
I use pi a squared.
Oh, it is
It's still a
cylinder formula. Oh, okay.
by the derivative of formula. Go ahead and find your EVT, go ahead and find your BSDT. And then you have everything that's in front of you, assign values to variables. And then see if you can piece this puzzle together. You're gonna have to use a couple of substitutions to find the missing piece and then continue going. Your DVT is negative, like your DVT.
Why would it be the same? It's so warm.
Yeah. So the water that's coming out, the rate that it's coming out is also the same rate that's coming in.
Oh, okay.
So that's why this negative and all of a sudden it's positive. Okay, so we start off with looking to see what we're finding, right? We're looking for DSDT. We need X, we need DXDT, but the problem doesn't quite give those to us explicitly. But they do give us some helpful information. They do give us surface area, they do give us dVdt. So how does that surface area help us out? Use this to find what? Find the X, yeah. So this can go here. We find the X, and the X is an element of what we need at the end. Okay. We also need dxdt. They don't give us dxdt, but they do give us dvdt. And that can help us solve for dxdt. And once we have dxdt, then we have that missing piece, and once we have x of dxdt, we get down to dxdt. If you want to kind of organize your information and just kind of figure out, wait, I'm missing this piece, how can I find that missing piece? And you're looking at your information to see, is there something that I can do to solve for that variable that I need? Any question with? Great. Okay, skip number 9 and try number 10. Guys, the key is included in your packet, so you can always double check your answer. Okay, set up your proportion equation. Does that look good for everyone? Everybody understanding why it's y over x plus y and not x over x plus y? So I'll point that out because that's a common thing that I see students miss. Make sure you put y over x plus y, not x over x plus y. Okay, this is the only equation that we need. Easier than cones. But it is still involving similar triangles. We cross multiply. Combine like terms. Okay, find the derivative with respect to time. What does 10y become? Right. Make sure that every variable gets impacted by time here. All right, let's talk about what these variables mean. dx dt is the rate of change of the person walking. dy dt is the rate of change of the what? Shadow length, yeah. And then if I add the two rates together, dx dt plus dy dt, it gives me the rate of change of the what? Tip of the shadow, yeah. So if we can find dy dt, then everything else will come easily. Okay. A man walks at a rate of 5 feet per second towards a street light. What information is that? dx dt. Anything special about that number? Negative because walking towards that x is decreasing in length. At what rate is the length of the shadow changing? So we're looking for dy dt. So if we use this equation and that value, we can find our dy dt. That's part A. Part B, rate of change of the tip of the shadow. dy dt plus dx dt. So therefore, what's that going to equal to? Negative 8. Okay. Use the space for number 9 for this, because I want to extend this problem a little bit more. Okay. Any questions so far? So 10C here. What's the rate of change of the area of the large triangle? So let's look at our large triangle here. So how do we build the area of a triangle? 1/2 base times height. How would you establish that based off of what we have in front of us? 1/2. Yeah. 16 is the height. What's the base? X plus Y. It's not X. What do you think a lot of students want to do here? X times Y. It feels natural, right? X times Y, but it's X plus Y, right? We want the length. We don't want the product. Do some cleanup. Can I keep going here? Can I get rid of the parentheses? Distribute. Now I can find the area, rate of change of the area. A becomes the EVT. 8x becomes AY becomes okay. Use the dxdt, dy dt from part A and B. Dy dt is -3. Dy dt is, sorry, ddt is -5, sorry. And what's our unit of measure here?
Feet squared.
Good. Area is feet squared. Fine. Okay. Good. So I think between yesterday and today, we were able to cover every type of problem that you're going to see on your quiz tomorrow. You guys all get that remind that I sent yesterday with all the list of topics? Okay. You'll get one of each problem, okay? Of each, 8 problems.
What formulas we have to know, we have to know.
Yeah, no Pythagorean theorem, no shadow problem,
In the triangle.
no area of a triangle, but everything else I'll give you. I'll give you the volume, surface area, area, circumference, cone, cylinder. All the geometric shapes I'll give you.
How do you go about it?
Okay, don't forget your phones.
Wait, do we do the service area of a cube?
No, I'll give all that to you. Guys, come up and get your phones.
Area of a triangle.
Right.
So
Pythagorean theorem.
Pythagorean theorem.
No that. No that. No shadow. Yeah,
Give me an example how you would use that area of the